Hey guys, I'm going to be working the 1-6 homework assignment, and I've already gone ahead and written down all the numbers and answered the first couple questions. I was right here on 17 and thought I better explain this one. So it is multiple choice, so hopefully you can pretty obviously see that the answer is going to be choice A. So that's a graph that looks like this, and I just wanted to talk for a second that the inverse means that all the ordered pairs are reversed. So if you were to list the ordered pairs of the original function, which you can tell that's the radical x function, so the square root of 1 is 1, the square root of 4 is 2, the square root of 9 is 3. So in your inverse function, you would be looking for a graph that had these points, and actually the inverse is f inverse of x equals x squared. The inverse of square root of x is x squared, or you could visualize the line y equals x, and there's a point. So you have your original point, and then you have this, and then you start getting a point on the other side of the line that corresponds and is the reflection over that line for your graph. So there's lots of ways to visualize that problem. In number 21, we're being asked to verify algebraically, show that f and g are inverses. So in number 21, f of x is square root of x minus 4, g of x is x squared plus 4, and we have a domain restriction there of x is greater than 0. So the way we verify is we do the composition. So I'm going to do f of g of x. So the square root, instead of an x there, I'm going to put x squared plus 4, and then minus 4. And the 4's will cancel out, so I want the square root of x squared, which I just get x. And that's the rule. If we do the composition and we get x for our answer, then they are inverses of each other. So the question is, do you have to do both compositions? That seems like a lot. And the answer is that I'm not sure, so I will have to get back to you on that. In the meantime, I'm going to go ahead and do both. So x squared, so I want to do square root of x minus 4 squared plus 4. So squaring this, I get x minus 4 plus 4, I get x. So it checks out. They are inverses of each other. So it's just to graph them on a graphing utility. So what I'm going to do is go into my Desmos, and I'm going to graph the square root of x minus 4, and then I'm going to graph x squared plus 4, and I'm only going to look at the x's that are greater than 0. Let's see, is there a comma on here that I can choose? Yes, look at that. X greater than or equal to 0. Let's see. Did I do something wrong? Let's see. Sorry, don't understand this. Maybe do I have to put parentheses? guess I can't remember how to restrict the domain. I know we did that on one of our activities, but so you'll just have to imagine the part of the graph that is to the right of 0. So anyway, if we're looking at the red section and the blue section and we visualize the line y equals x, we can see that the blue is a reflection over that line of the red. Okay, so now let's keep going. And in number 23, we're going to be asked to do something pretty similar. In 23, the functions are f of x equals 1 minus x squared. G of x is 1 cubed. G of x is the cube root 1 minus x, so I'll do f of g of x. 1 minus, and instead of an x, I'll put in the cube root of 1 minus x cubed. And then cube root and cube counteract each other, so I get 1 minus x. So 1 minus 1 is 0. Let's see. Oh, 1 minus 1 is 0, and minus x is just x. Okay, so that worked out. I think the times when I would do both f of x and g of x is if it didn't work out. If f of g of x didn't work out to be x and they weren't, I was about to have to say they're not inverses, then I would probably use g of f of x to check myself. And that way you have two ways to tell if you made an algebra mistake. So I'm going to tear this off and go with number 27. So in number 27, the directions are 27 and 31. Actually, there's a lot of work for those, so you have to verify that they're inverses algebraically, graphically, and numerically. So let's just start with algebraically. F of x equals x cubed plus 5. G of x. Okay, this one's very similar to the last one. So f of g of x is the cube root of x minus 5 cubed plus 5. So once we cancel out the cubes, x minus 5 plus 5 equals x. So there I have verified it algebraically. Now let me go ahead and verify it graphically. So I need to try and find a cube root on this thing. So let me see if there is a cube root in here somewhere. There's an n root, so I have to put my 3 in there. And then I can go down and underneath the radical symbol, okay, it looks like I'm graphing g first. Alright, so cube root of x minus 5, and then x cubed plus 5. Oh, maybe I can use this caret symbol. X to the third. Yeah, so I used the little, right above the 6 on a keyboard is the caret, and that is going to be how we raise things to different powers here. Okay, plus 5. Let me get rid of this. Okay, so, and then, oh darn it, I hit erase and not enter. Okay, x raised to the third plus 5. Enter. Okay, whatever. So y equals x. So I can see by graphing those three things that they are a reflection over that line. So I just verified it graphically, and then algebraically or numerically. So what I want is to look at the table for the first one, so I can kind of see these points here, and then I want to look at the table for this one too. How did I do that? There we go. Cube root of x minus 5. Did I type everything in correctly? Yes. X cubed plus 5. So negative 2, negative 3. Alright, let's just say I really wish I had a TI calculator where I knew how to look at the table. Here I really want this table to be extended, and I just don't know how to do that on this calculator. So okay, well, I can click on the graph, negative 2, negative 3, and then negative 3 and negative 2. So I can see where the points for the different locations are reversed. So I'm going to call that a victory. If you have your calculator, feel free to look at the table and use that way. Alright, let's keep going. In number 31, same thing. Let's see, do we need to sketch the graphs? Let me go back. And so here was 5, and here is 5. So what I have is a sideways cubic and a regular cubic. And then I could sketch the line. Okay, in number 31, f of x equals 2x, and g of x equals x over 2. So verifying f of g of x, so 2 times x over 2 equals x, so that works. And then graphically, 2x has a slope of rise 2, run 1. So like that is my down 2 over 1. So that's the steepness of that line, and then the x over 2 is like a 1/2 x, so up 1 over 2, down 1 over 2. So that's the steepness of that line. So if I visualize my y equals x line running right through there, I can graphically verify, and then so if I do a table of values for my original function at 0, 0, 1, 2, 2, 4, and then I do a table of values for my g of x, 0, 0, 2, 1, 4, 2, I can see that it follows the rules for inverses. Alright, number 40. In number 40, we have to determine whether the graph is out of a function. If so, determine whether it's one-to-one. So let's take a look at number 40. Number 40 is a parabola, and it is located, it has a vertex of like 2, -1-ish. Is it a function? Yes. Is it one-to-one? Well, how do we test for one-to-one? Function is the vertical line test. One-to-one is the horizontal line test. We say no, it's not one-to-one. Therefore, you would not be able to find an inverse of that function. Number 53. Use a graphing utility to graph the function. Use the horizontal line test to determine whether it's one-to-one and thus has an inverse. So in 53, our function is g of x is x plus 5 cubed. And so to graph that, I'm going to go back to Desmos. And I'm going to get rid of these guys. And I want to do x cubed. No. X. Alright, x plus 5. And the whole thing raised to the third. What? Oh, I forgot to hit shift on my parentheses. Okay, there we go. X plus 5 to the third, and that is a horizontal shift of 5 units to the left, which is what I would be expecting. So if I use the horizontal line test on that, which I can even show you a few horizontal lines. Wait, can I? Y equals 4. Let's see, y equals 4. Okay, yeah, so there's some horizontal lines. Y equals 2. Plus 2. Anyway, you get the idea. Y equals 2. That one's in green. So as I draw horizontal lines across my graph, there's no place where it touches twice. So therefore, let's see, what was the question again? Number 53. Therefore, it's one-to-one, and thus it has an inverse. Notice it doesn't say you have to find the inverse. So that's nice. Number 65. Let's see the directions. Determine algebraically whether it's one-to-one. Verify it graphically. If it's one-to-one, then find the inverse. Okay, so this one we have to do that work. Alright, so f of x equals x plus 3 squared. And we're given a domain restriction, x is greater than or equal to -3. So let me go ahead and graph this real quick. So this is a horizontal shift of 3 units to the left. So 1, 2, 3. So the only thing is we're given this restriction. So I can only graph the portion that lies on this side of the -3. So that's only going to be half of my parabola, which means that it will pass the horizontal line test. So I verified that my function was one-to-one graphically. We want to do that algebraically. Okay, so finding if a function's one-to-one algebraically was an example that I didn't show you yesterday. So you can look at example 7 on page 64. And the way you do that is you take your function, x plus 3 squared, and on one side you're going to substitute an a, and on the other side you're going to substitute a b. and then you work out all the algebra, and you see what cancels, and if you end up with a equals b, then it's 1 to 1. So this should be fun. So a plus 3 squared is going to be a squared plus 6a plus 9. And this one would be b squared plus 6b plus 9. So automatically I can subtract off the 9's. And then, so I have a squared plus 6a equals b squared plus 6b. So how do I end up with a equals b? Okay, I want you to forget everything I just wrote. If I knew how to back this video up and erase it, I would. So, to verify that a function is 1 to 1 algebraically, all you have to do is show that it has an inverse. So, even though we see that it passes the horizontal line test, if we want to do the algebra and find the inverse, then we will be all set. So we know how to do this. So we want to get y by itself, so square root both sides, and we get square root of x equals y plus 3, and then we subtract 3. So square root of x, and this 3 is outside of the radical symbol. So that is just going to be your standard radical function, but shifted 3 units down. So there it is. We can see visually that it is on opposite sides of y equals x. And does that answer the full question? Let's see. Verify it graphically. If it's 1 to 1, find the inverse. We did it. Alright, so moving on. So let's get these last three or four problems. Got number 67, 71, etc. Alright, number 67, we are going to work, it's similar to the last one. So f of x equals square root of 2x plus 3. So I can see that's a radical function. It's 3 units to the left, and then this 2 is a horizontal compression. So not sure that any of that matters, but it's just good to review our transformations of functions. So let's go ahead and see if we can find an inverse. X equals 2y plus 3. So this time I'm going to square both sides. So x squared equals 2y plus 3. Subtract 3, subtract 3. X squared minus 3 equals 2y, divide by 2, divide by 2. Okay, so there is the inverse. I was able to find it, so it must be 1 to 1. I do have a restriction on my domain for this one, so x has to be greater than or equal to 1.5. Negative 1.5, sorry, 2 times negative 1.5 plus 3 equals 0. So we have to give that same restriction on everything. So, and let's go ahead and look at that algebraically. So this one, I said it would be 3 units to the left and compressed horizontally by 2. So just kind of like that. And this is a parabola, so I'm going to distribute this 2 or divide it out. So it'll be 1.5 units to the right, and it'll be a vertical stretch. So 1.5 units is over here. No. Look at that. That's not inside the parentheses. That's a 1.5 units down. So it'll be something like that. So graphically they're on both sides. Now you can of course use your graphing calculators. You do not have to do all of this in your head. So it's 1 to 1. We found the inverse. We graphed it. I think we're good to go. In number 71, we have a different set of instructions. Find the inverse algebraically. Graph them both. Describe the relationship. So here I was thinking this unit would be a challenge for you guys, but I'm hoping that you're going to find it quite easy. So let's solve back for y. Be helpful if you could see. So y equals x plus 3 over 2, and the graph of that. So 2x minus 3, I'm going to go to the intercept, -3, and I'm going to rise and run 2 and 1. So the original graph looks like this. And then I'm going to rewrite this in slope-intercept form. So that'd be 1/2 x plus 1.5 or 3/2. So I go up to my y-intercept. My slope is up 1 over 2. And then again, description. Those are two lines that are symmetric with opposite slopes about the line y equals x. So if I'm really truly answering the question, it's a reflection over y equals x. So that's a description of the lines. Okay, and number 73, same set of instructions. So this time we have a higher order power, so y equals x to the 5th. So if I'm solving for the inverse, x equals y to the 5th, 5th root, y equals the 5th root of x, and I have no idea what these graphs look like, so I'm going to go back to my graphing utility. So let's see, it's a Desmos. Let me get rid of all my other graphs. So we want to do x raised to the 5th. Oh, it looks like a big cubic. Okay, well that's simple enough. And then we want to do a 5th root of x. So there we go. So we had to, the directions say, let's go ahead and graph those. Let's see. Alright, and describe the relationship. Well, I think they're symmetric about y equals x. And in what way are they symmetric? They are a reflection, which of course you cannot see me writing any of that. So there we go. Okay, and are we on the last one, number 81? Let me see if I can fit it on this paper. 81, we have different directions, yes, of course. Okay, restrict the domain so that it's 1 to 1 and has an inverse. Then find the inverse. Okay, so if you've been noticing in all these problems that we're doing, a lot of times they restrict the domains on the parabolas, and that way only half of the parabola is showing, and then it will pass the vertical or the horizontal line test. So x minus 2 squared is a parabola that's shifted 2 units to the right. So how could I restrict the domain so that it would be 1 to 1? Well, so if the original function is a parabola, 2 units to the right, then if I could restrict my domain so that just half of that parabola was showing and the other half was not part of the equation, then it would be able to pass the horizontal line test. So that's what I'm going to do. I'm going to restrict the domain to say, okay, I only want x's that are greater than or equal to 2. And then find the inverse. So we do y equals x minus 2 squared, x equals y minus 2 squared, square root. So square root of x equals y minus 2 plus 2. So our final function is going to be y equals square root of x plus 2. And so that's going to end up being the radical function plus 2 is shifted 2 up. So if our original function is just this part, then the radical function shifted 2 up looks like this. So you can kind of see that they are inverses of each other. So you know that the inverse of squaring something is square rooting. Well, it works for it to be the inverse as long as you only look at half of that graph. And that's it for 1-6.